What will happen if sodium is reacted with water? We know that reaction is very violent. Means whenever sodium reacts with water, what is going to happen? That sodium is reacted with water and you are getting NaOH and the hydrogen gas. Okay, this is what is the thing what is going to happen. I will call this reaction to be irreversible. Why? Because I can't get my back sodium. That is why I will call this type of reaction to be irreversible. So here in a whenever there is a reaction, there are two types of reaction. One is irreversible. These are the category of the reactions where we can't get the product. The reason may be anything. Reason for the irreversible thing could be anything. Like it could be a open system. If system is open, then the possibility is that there is because of which we can't get the product back, right? For example, calcium carbonate. Okay, calcium carbonate when reacted with when it is decomposed. Okay, when it is decomposed, what we get is calcium oxide and the carbon dioxide. If this carbon dioxide which is formed, it just escapes as a gas. If this carbon dioxide is escaping as a gas, that time we don't have the possibility that we will get the calcium carbonate back. Or it could be a reason why this is escaping because the system is open, or even if the system is closed and if there is a precipitation taking place. For example, AgNO3 and the KCl. If this is the case, then what we are going to get is potassium nitrate and AgCl solid getting precipitated. Okay, these are the products because it is getting converted to the solid. So we can't get back this AgNO3 and KCl. So these are the conditions. Reason is one if it escapes as a gas, mostly happens in the open system, and if it is getting precipitated as a solid, this is possible even in the closed system. In these cases, the reversible reaction is not possible. We will call these reactions to be irreversible. So irreversible reaction doesn't lead to equilibrium. So there is no equilibrium taking place in a irreversible reaction. There are certain reactions. I will just write the names of the reaction. I will just write the reactions. Let's take this AgNO3 and sodium chloride getting converted to NaNO3 and other is Ag. So the product, these are the reactant and the product. This is solid what we are getting. This is aqueous, this is solid. This is I guess aqueous. Right. So here the AgCl which is formed, this is forward, means this is, I will show this arrow in this manner. In this direction, the equilibrium is very less. It is negligible in the backward direction. Although it is equilibrating this reaction, it is not of the significant, it is the change is not significant. Okay, here the reversible reaction is not significant. So this reaction is also not considered to be equilibrating because 99% of the reaction going in the forward direction, 99.9 and 0.1% will be in the backward direction. So this is almost considered to be a forward reaction only. Like there are one more example this way, which is forward reaction and which slightly reverse back is BaCl2 and what is this? This here also the equilibrium is very less, not equilibrium, backward reactions. Like backward reaction means from product to reactant. Always remember the forward reaction, whenever we will be using the word forward reaction, is from product is from reactant to product, reactant to product. Okay, from left to right. And backward reaction is from product to reactant, from right to left. Okay, these reactions are not equilibrium, these are the irreversible reactions. Let's understand what is a reversible reactions and the equilibrium also. So we are understanding reversible reactions and also the equilibrium. Let us consider there are reactant A plus B getting C plus D, and C and D again it is reacting, again they are reacting, again they are reacting to give you back A and B. This is possible. One example I will write for such type of reaction is a N2 and a hydrogen gas. This is also a gas and this is also a gas getting converted, getting like under certain conditions of the temperature and pressure, they are going to get converted to ammonia, right? So this is the reaction. Here there is a formation of the ammonia. This is reversible reaction because whatever ammonia will be formed, a certain after certain change, after formation of certain amount of the product, there will be a reversible decomposition reaction which will be giving you a hydrogen and the nitrogen. This is the equilibrium reaction. Now what happens in the equilibrium? Chemical equilibrium, when we say that um, let's understand it this way only. There is A, there is B giving you product C and D. It is right over here. Let's understand this with respect to the graph. I will just write rate of reaction. Now what does this mean, rate of reaction? Rate of reaction tells about the speed of the reaction, how fast the reaction is taking place. Usually rate of the reaction is directly dependent on the concentration of the reactant. Always remember that rate of the reaction is directly dependent on the concentration of the reactant. Let's say this is the reaction, then here it is dependent on the concentration of A and the concentration of B. More is the concentration of the reactant, more is the speed of the reactant. So at time t is equal to 0, and let's say this is a time coordinate in this direction, at time t is equal to 0, it will have maximum rate. Okay, the rate of this will be maximum. After some time the rate is going to fall, the speed of the reaction will be of this, right? After some time the rate is again going to fall, speed is going to fall because the reactant is getting converted to the product, right? Because rate of the reaction is directly proportional to the concentration, and concentration is decreasing because reactant is getting converted to the product. Let's say at initially this was the concentration was 10, this was also 10, and after some time, since the reactant are reacting and getting converted to the product, it has reduced to 8, then 9, then 7, then 6. Means with time the concentration of A and B is decreasing. So what is going to happen to the rate? Rate is also going to decrease. And let's say this is the curve which I can draw. This is the curve which I can draw. For the reactant, this is the reactant rate which I can draw. Now at the same time, there was a 0 rate of reaction of the at 0 time. This is a at time is t is equal to 0. This is a rate of the product because there is there was no any speed of the reaction. There was no any speed for the reaction for the product to get converted to the reactant, because there was hardly any, like if this was 0 and 0, there is no any formation of the product. How the products are going to get react, isn't it? So at that time it was 0. As the product started forming, what has happened, that they also started reacting back, means whatever C and D were formed, they started reacting back to give you A and B. So this is called as a backward reaction. So rate of the backward reaction is also increasing. Like this point where the rate of the forward, I will write this is product and this is reactant, right? So this is the rate of the product and this is rate of the reactant. This is rate of the forward reaction and this is rate of the backward reaction, this curve. So at this time, this is the point where I can say that it is in equilibrium. From here, the reaction started to be in equilibrium. Now there may be a question which may arise in your mind. At equilibrium, the concentration of the reactant and the product will be equal. Not necessary. Okay. In some coincidental cases, there may be the concentration of the product and reactant may be equal. But it is not necessary that the concentration of the product and the reactant will be equal. It will be constant. Concentration of the reactant and the product at equilibrium will be constant. It won't be varying, but it won't be equal. Now, what is the meaning of constant but not equal? See, let's say this is A plus B. This was a concentration of reactant A and reactant B at time t is equal to 0. At time t is equal to 0, where reaction was just started. After some time, let's say this reaction comes to an equilibrium after 10 minutes. So after 10 minutes, the concentration may not necessarily be 5, 5 and this is to be 5 and 5. No, this is not the thing. It may be anything. For a simplicity, I can consider that the maximum of the reactant are getting converted, means over here hardly 2, this is 2 and this is 3 is remaining. Okay, and here the concentration of reactant has increased to let's say 7 and here it is increased to 6. Somewhat this way I can say. Okay, these are the concentrations of the reactant A and B and C and D, the concentration of the product C and D. Right? Concentrations of the reactant for the different reactant and for the different product are different. They are different. But these concentrations are going to stay, like concentration of the C is going to remain 7 only, concentration of the D is going to remain 6 only, concentration of B is going to remain 3 and concentration of A is going to remain 2 only in this reaction at equilibrium. Why? Rate of forward reaction. See, rate of forward is equal to rate of backward. That is what we say at the equilibrium, right? So at equilibrium, rate of forward reaction is equal to rate of backward reaction. The only speed is equal of getting converted, and it is not that at a after converting certain amount of the reactant to the product, that time only, after that time rate is becoming equal to maintain this concentration. So here concentration of the reactant and the product may not necessarily be same, but the speed of the forward reaction and the backward reaction will be equal, because that speed, that point, equilibrium point, depends upon the reaction. It may be a 10 minutes, it may be a 15 minute, 20 minute, 1 hour, whatever it may be, it depends upon the reactant. Okay, so this is the thing about the reversible and the equilibrium reaction. Rate is going to depend upon the concentration. Now here, one more equation I will give. This is for the forward reaction. This is forward. And for the backward reaction, rate will be, I will write this to be x and y. Okay, x and y. Let's take this to be a stoichiometric coefficients only. And let's take this to be A and B. This rate is directly proportional to the concentration of C and concentration of D, A and B, for the backward reaction. Backward reaction. So these are the two rates, the forward and the backward. Okay, here just a small change. This is C and D. C and D. So here, let's go ahead with the topic, law of chemical equilibrium and the equilibrium constant. Let's start with this basic equation, reactant A, and it's A, small a is a stoichiometric coefficient, reacting with a B, and this is small b, is in equilibrium with C and C, D and this capital D. These small letters A, B, C, D are the stoichiometric coefficients. Okay. So ask one question to yourself, whether this equilibrium, whenever any reaction takes place, that equilibrium is going to take place at initially or after some time. The answer will be the equilibrium will be taking place always after some time. Okay, for particular reaction there is a particular time to get equilibrate. So if I am writing, what did I say, that speed, right, the speed of the reaction, we are going to understand what is equilibrium constant over here. Our aim, why we are understanding chemical equilibrium, first is equilibrium constant, right? So the equation will be very simple, and the deriving and understanding the way we are deriving, it is also very simple. So forward reaction, what is the forward reaction? This reaction could be divided into two. I will call one to be forward, A plus B getting converted to the C plus D, and other will be a backward reaction, that is C plus D again reacting back to give you A plus B. So rate, speed of the reaction is always dependent on the concentration of the reactant. So I will write that rate is dependent, right? I will say that rate of forward reaction, F I am writing, or let's write this forward. Rate of forward reaction is directly proportional to the concentration of reactant, right? And the rate of backward reaction is directly proportional to whose concentration? Backward means you can consider there's C and D as a reactant now. For the backward, for us it is backward reaction. For reactant, for this C and D, it is they are reactant and giving you back A and B. So here for the backward reaction, it is a concentration of C raised to concentration of D, right? So here forward reaction, whenever we write a forward reaction, I just should have kept more space, so I will write rate backward is directly proportional to the concentration of C raised to C and D raised to D. So here, this, to remove this proportionality constant, I will say that rate, instead of forward I am just writing, let's write it forward. I am removing this proportionality sign, I am introducing one constant K F, and this is concentration of A and concentration of B. This is equation 1. I will get another equation, rate backward is equal to KB. KB is KB for backward, C raised to C, and this is D raised to power D. So this is my equation 2. So what happens? At equilibrium, rate of forward is equal to rate of backward, right? At equilibrium, rate of forward is equal to rate backward, right? So I can equate, so therefore I can equate these two equations. So equation 1 and 2 I am equating. So what I will get? I will get Kf into K backward is equal to C raised to C and D raised to D, right? So if I write this Kf upon Kb, these two constant, this is also constant, this is also constant, and I am rearranging this equation, what I get is C raised to C and D raised to D. This is what I am going to get. So this is constant, this is also constant. I will just mention this to be a Kc. That is equilibrium constant. This is now new constant, that is equilibrium constant in terms of concentration. So this is how we understand that this is equilibrium. So this is equilibrium constant in terms of concentration. So for these reactants, what we write? A concentration of the product upon concentration of the reactant raised to its stoichiometric coefficient. This is how we write the Kc. That is equilibrium constant. So equilibrium constant is Kc. Kc is equilibrium constant in terms of concentration. Remember this. Okay, let's understand this. If there is a, let's say, formation of the ammonia N2H2 giving you 2 moles of ammonia, and I'll put this 3. So for this, let's take this is gas, and this is also a gas. Kc, equilibrium constant for this reaction, will be a concentration of product, that is concentration of NH3 raised to its stoichiometric coefficient upon concentration of N2 raised to 1 and concentration of H2 raised to 3. This square brackets always remember, always represents a concentration. Always remember, in chemistry, square brackets means it is a concentration. So this is how I will represent the concentration or the equilibrium constant for this reaction. Next, understand equilibrium constant in terms of the pressure. This was in terms of concentration. So we are learning equilibrium constant in terms of pressure. So I will write equilibrium constant in terms of partial pressures represented as Kp. Kp will be the representation. Means, for example, if there is a gaseous reactant A, gaseous reactant giving you product, right? So here, how I will represent a equilibrium constant in terms of the partial pressure is that Kp instead of C, I am in terms, instead of C, what I am writing is P, that is C raised to, sorry, here in terms of partial pressure. So partial pressure of C, right, raised to its stoichiometric coefficient, partial pressure of D raised to its stoichiometric coefficient divided by partial pressure of A raised to A, and this is partial pressure of B raised to B, right? This is how I am going to represent. Means, for example, if these are all gaseous reactant, right, here I want to represent a equilibrium constant in terms of partial pressure, then it will be Kp will be is equal to partial pressure of NH3 raised to power 2 divided by partial pressure of the nitrogen multiplied by partial pressure of H2 raised to power 3. This is how we are going to represent. So this is Kp and Kc.